Hello everyone, this is Tzu-Han. I'm the PhD student from Georgia Tech EC department. In this presentation, I will show you an interesting way to perform hybrid structure of noise shaping SAR with sampling noise cancellation in a high ENOB and energy efficient manner. So this is my self-introduction. I graduated from National Taiwan University in 2018, and I joined Georgia Tech as a PhD student from 2019. My current research interest includes digitally assist noise shaping techniques and the mixed signal circuit design. So my talk will follow this agenda. I'll first go over a brief background of the noise shaping SAR ADC, and then I will give a quick review on the challenge of it. I will talk about their issues and the need for a new architecture for noise shaping SAR. We will then present our approach of hybrid structure and the KD over C noise cancellation. And then I will show you some circuit implementation as well as the measurement results. Finally, I will draw the conclusion. So please allow me to begin. Although ADC have been an essential part of almost all electronics systems, the quest for better ADC design is always ongoing. There is a strong driving force, which is the booming of the IoT. So many applications, for example, body implant circuits, biomedical sensing circuits, they do not require very high-speed ADC, but rather they need the ADC to be high on the dynamic range. Moreover, they must also be very power efficient to work with the low energy power source. Therefore, the aim of this type of ADC should contain both high resolution and the low power characteristic. So the question is, what can our candidate be? So first, for high resolution candidates, the traditional way is to use the delta sigma ADC, but they are actually too power hungry. So if we want to shoot for a low power design, we can rely on the SAR ADC. But yet, they cannot work in a relatively high resolution very well. Therefore, the recent trend is to build a noise shaping SAR ADC, which it combines the merits of the delta sigma ADC and the SAR together. So in short, the noise shaping SAR contains only capacitor arrays, switches, comparators, and SAR logic. And then we know that the noise shaping can effectively suppress the quantization noise. So it can improve the resolution while keeping the comparator in low power and then making the DAC and the SC loop filter simple as possible. So in other words, our goal in design the ADC aims to the high resolution and the low power concurrently. Now, let us take a look at the ADC's array plot. So recently, noise shaping SAR ADC show their ability to be in the ADC frontier, and then they have achieved the 180 dB figure of male line. And we found out that they had particularly good performance at the lower ENOB range, which by means the ENOB that are smaller than 12. But then when we are trying to shoot for a higher ENOB, there will be a recessive of power, which makes us wonder what the reason is. And it turns out there are actually two limitations of the energy efficiency in the high ENOB, which the first one is the high order noise shaping. The high order noise shaping is not trivial. So existing work, what they did is they use low order, and then therefore they requires a high oversampling rate. And then for a high oversampling rate, more digital power will be used, therefore resulting in low energy efficiency. So another troublesome factor that noise shaping SAR has encountered is the thermal noise. Even one can use the high order noise shaping to shape the quantization noise, the KD over C noise is not taken care of. It will quickly dominate and limit the performance of the ADC. So for most existing design, they just use sufficiently large CDAC, shown right over here, or large oversampling rates to make sure the KD over C noise is low enough. As a result, the power and the area goes up very fast, bringing the impact to the energy efficiency. And then on the top of this, we must also realize that large CDAC will be hard to drive, which makes the input driver harder to design. So now we know there are several issues of the noise shaping SAR ADC needs to be taken care of. One is to achieve the higher order of the noise shaping SAR and then the low OSR. Another one is to break the KD over C noise barrier. So as a result, our solution goes to the hybrid arrow feedback structure and then the KD over C noise cancellation, which will be introduced in the later slides. So now what I would like to show you is our proposed arrow feedback CIFF structure for the noise shaping SAR. I will begin with some prior artwork and then express our design. So there are actually different ways to implement the noise shaping SAR. One of the tracks that arose and become popular recently is the error feedback structure. In this figure, we show you how error feedback actually works. It directly extracts the quantization noise, and then it got transferred onto the FIR filter, and then it got combined in the next conversion. So the error feedback shows several advantages, which the first one is that it has a simple FIR filter, so it can achieve the OTA list, which it is very energy efficient. So second, it can achieve the NTF0 easily, and then bring the good noise shape. And error feedback has issue as well. The sensitivity is not good in pushing in high order. And let me introduce that in the next slide. So basically, the error feedback contains the amplifiers and switch capacitor circuits, and high order noise shaping basically is the thing that we want to push for. However, higher order means that the higher gain is needed. And then the higher gain makes the amplifier hard to design. And another thing is that as the order goes up, and as the gain varies, more of the zero from the NT-F will be affected, which makes the overall will be more sensitive. Here we show you another interesting prior artwork, which is the cascaded error feedback structure proposed in the 2020 ISCC. So basically, they use an intriggering way of the error feedback implementation. They use an inner loop of the error feedback structure to pre-shape the quantization noise for the outer loop of the error feedback structure, which brings several advantages. First, they can achieve the high order NTF, and second, they can keep the circuit implementation with the low complexity. So they don't need a high gain amplifier, and their NTF coefficient is that sensitive to that of the single loop case. But still, they have some SQ fluctuation. That is to say, if the two of the amplifiers right over here would affect all the zeros. And the second amplifier may also seize the offset from the first amplifier, which it is relatively low offset tolerable. And then this basically limits the gain of the amplifier, which it actually has noise penalty. So basically, from the previous single structure of error feedback, make us think about maybe we can include the hybrid structure right over here. So our goal basically aims to that we want the high order noise shaping, and then we want to keep the robustness, and finally we want our SQ fluctuation even smaller. So basically, if we want to achieve the high order noise shaping directly, apply the high order onto the FIR seems not to be reasonable because it's going to be sensitive. And then, can we pre-shape the quantization noise and keep the robustness at the same time? The answer is yes. So what we have done differently right over here is that the previous work only focused on the error feedback, but if we think about that, we can actually incorporate another noise shaping SAR type into our design. So basically, we have chosen to incorporate the CIFF structure and then combine the merits of the error feedback and CIFF of the PVT robustness together. So if you think about it, the idea is like a noise coupling in an intriggering way. So based on the graph, can we maybe merge the part of the error feedback and the CIFF together, which I means the basically this part and this part. So the answer is yes. And then by this point, the design actually emphasizes several advantages. So basically, the first thing is that with the hybrid structure, we can use just a single amplifier to share the same VRES, or saying in different ways, since the error feedback and CIFF shares the same VRES, we can basically use a single amplifier. And then another thing is that since the VRES right over here is a high pass, so for the amplifier, it sees no offset, and therefore we can use a larger gain of the amplifier. So what we have achieved right over here is our first goal. So we have achieved the third order of the noise shaping with the error feedback and the CIFF. And then the second goal is that we have used the CIFF path to achieve the PVT robustness. And with the PVT robustness, we can achieve the less SQ-now fluctuation. So let us take a look at the graph right over here. So previously with the cascaded arrow feedback, it shows decent amount of the SQ-now improvement with minus 20 and 20% of the coefficient variation. But if we take a look at our EF and CIFF structure, we see that we have even more SQ-now improvement, even when the coefficient variation is large. We still have a total amount of over 35 dB of SQ-now improvements. So we can implement the design in this way. The residue will be amplified with the gain G, and then pass it on to the arrow feedback and the CIFF filter, which these two of the filters are passive switch capacitors that are able to reduce the power. And then we can sum the results together without any active components. So now let us take a look at our contribution in the KD over C noise cancellations. I will begin with some previous works and then explain our works in detail. So now before we talk about the noise cancellation, the people traditionally think that the KD over C noise is random and is a fundamental limit. But by probably using the bottom plate sampling, we can make it as an offset-like extractable quantity. So what we have shown you right here is the JSCC 2014 paper. What they use is the active noise cancellation of a sampled KD over C noise, applied it on the switch capacitor circuit. And then making advantage of this structure, Tsinghua University have shown us how we can implement it in a standard SAR ADC. So it will be explained in the next slide. And then what Tsinghua University did in the ISSCC 2020 is that they leveraged the preamp and the series capacitor together in the comparator. And then for this method, it took the advantage from the bottom plate sampling, since the bottom plate sampling rely on the two timing clock of phi 1 and phi 2. So what this work does is that it used the phi 1 and phi 2 turn-off time difference to capture the noise replica. So basically, at the T1 closing time, the VNS1 is kept before the preamp, which the CDAC will provide it a noise replica and put it at the left-hand side of the preamp, ready to be transferred. And then at the T2, VNS1 will be transferred it onto the series capacitor, and eventually it will be canceled out with the previous VNS1. But this method actually has two defects, which the first one is that since the preamp is constantly on in order to be fast, so it is actually very power hungry. And then the next thing is that this method, although it is applicable to the standard SAR ADC, but it is not directly applicable to the noise shaping SAR. So the reason will be given in the next slide. And then if we draw out the signal flow, we can see that from the previous case, we can see that the noise replica injected directly into the comparator will be shaded with the quantization noise. Thus, it will not cancel out the KD over C noise. So can we directly apply it to the noise shaping SAR? The answer is no. So what can we do about that? So what we think about it is that maybe we can move the KD over C noise cancellation or the noise replica outside of the comparator or before the comparator. And then can we reuse the noise shaping SAR hardware? The answer is yes. Let us see how we can actually apply this. So basically what we did is that we used the original structure of our arrow feedback and CIFF hybrid structure and then incorporate another sampling noise cancellation capacitor in parallel form. And then what we can do also is that we can reuse the residue amplifier, which is very hardware efficient. So now let me show you how it works. So for simplicity, let us just show the only arrow feedback path right over here. So the function will not change, even the CIFF structure for our design is neglected here. So noise shaping SAR can roughly be divided into two ballpark phase, the normal SAR conversion and the residue processing after. So let us focus on the VREF extraction. For the VREF processing part, nothing got changed, so we just show it right here as the first step for the sake of the cycle completeness. And then now let us ignore the input signal right over here and only focus on the noise. So after the VREF processing, we begin with the next cycle sampling. So now we can see how the sampling noise cancellation works. So here we once again leverage the two bottom plate sampling to extract the KD over C noise on the CDAC. As the falling edge of the phi1, the noise inside the CDAC as well as the noise in the CEF is frozen. So the voltage on VNS1 will be set up at the input of the comparator and the residue amplifier and be ready to transfer. And noted that the noise of the CEF is also being put in the VC. All right, so once we fire up the residue amplifier, by the end of the phi2, we will have an amplified replica of VNS1 stored on the capacitor of the CSNC. So this capacitor is an additional capacitor that it is connected in parallel with the error feedback filter and the CEF. Then finally, as the conversion starts, we merge the CSNC and the CEF as well as the error feedback filter all together to perform the normal feedback summation. And because of the charge sharing, we can inject the replica back into the signal path, and then we can use the charge conservation to calculate the voltage at the input of the comparator. And at the end of the SAR conversion, we can see that the VNS1 will be factorized by the 1 minus G times KNC, where G right over here is the gain of the residue amplifier, and then the KNC right over here is the attenuation ratio given by all this capacitor. So our goal is to design the reciprocal of the KNC such that the G times KNC equals to 1. That means the VNS will be eventually cancelled out. So by this point, we should be able to see the advantage of the proposed noise cancellation scheme. So first and foremost, it is simply if you use the native block of the error feedback noise shaping SAR, it only contains an extra block of a capacitor and two switches. So it is very hardware efficient. And second, because we use the residue amplifier for the noise rejection instead of a comparator preamp, the comparator can be much simple. And then more importantly, unlike the preamp that needs to work on all the time, in the previous case, in our case, our amplifier can be turned off during the SAR conversion. So as a result, this brings a significant power saving compared to the previous cancellation scheme. And so we therefore achieve our two goals, the low power and the hardware suitable for noise shaping SAR. And then here, what I want to highlight is that it is also worth to mention that yet another advantage of the proposed SNC is that it is inherently flicker noise rejected. So we can see that there are two terms here, in fact, contains the amplifier noise, and they have the opposite polarity. So this will cancel out because they are correlated flicker noise. And then one is the error feedback phase, while the other one is the KD over C noise extraction phase. So now let me show you some circuit implementation in the following slide. So as a proof of concept, we have developed a third-order noise shaping SAR in a hybrid structure with the employ of the proposed noise cancellation techniques. So it is worthwhile to note that although the EF and CIF is used here, but the overall proposed SNC technique can also be applied to other noise shaping SAR type. So what I would like to show right over here is that we have is our CDAC configuration. So we have used the split capacitor array to keep the input capacitor small enough, and then with the unit capacitor size of 6 femtofarads. And then right over here, we show you the error feedback path and the SNC capacitor. So there we have used the ping pong delay to control our second order FIR filter. And then the highlight over here is that in our design, they are fully passive switch capacitor, which actually saves us power. And then likewise for the switch capacitor in the CIFF structure, they are all also passive switch. So right over here, we show you all the capacitor parameters and the gain, which shows our overall NTF construction given right over here. And then for our residue amplifier, we can use a dynamic amplifier without any problem. Since the previous case, they will have to rely on a constantly on amplifier. And then the previous case also needs an extra timer or a closed loop configuration. But in our case, we can just use an open loop floating inverter amplifier without any problem. And then we can use this as an open loop fashion with a self-quench and a gain self-stabilized characteristic. So this is the photograph of our design as shown in the figure. Our total chip area is 0.4 millimeter square, and the design is with the 65 nanometer technology. The interesting we can observe right over here is that for the previous design, the CDAC usually occupies more than 70% of the total area. But in our design, thanks to the noise cancellation, the CDAC only occupies less than 50% of the total area. And then what I would like to show you right over here is our measurement results. For the measurement, let us take a look at the spectrum first. So we have achieved the 6 dB of the noise level and with the SNC on. And then we have also achieved a SNDR of 6 dB and the SFDR of 11 dB. And then right over here, the dynamic range shows that we have achieved a 6 dB as well. And then for the power, we have achieved 120 microwatts with 17 microwatts of digital power. The interesting thing is that we use a 65 nanometers technology. So if we use a even better technology, we can have a even smaller digital power. And then here we measure the temperature and supply voltage variation. Our temperature is measured from -20 to 80 degrees. And then the supply voltage is measured from 1 volt to 1.2 volts. So the SNDR and the dynamic amplifier gain, which SNDR is kept within 1 dB and the dynamic amplifier gain is kept within 10% in both cases. And then here we show you the measured NTF coefficient and the SNDR with 5-chip variation. So the SNDR is kept within 1 dB variation, and then the NTF coefficient is kept within overall 10% variation. So now I would like to show you the performance summary that our performance, thanks to the KD over C noise suppression, we have achieved 0.8 of input capacitor, and then we use a single amplifier in an open loop fashion to achieve a third order of the noise shaping. And then eventually we have achieved the Schreier figure of merit with 183 dB right up here. So let us go back to our performance summary. So basically we have achieved over the figure of merit line of 180, and then with a oversampling rate of only 8 and 0.4 picofarads. And then it shows that our performance outperformed the previous artwork. And then finally, allow me to quickly summarize a few takeaway points. So in today's presentation, I give an overview of the noise shaping SAR ADC in a high energy, high order implementation. And then we proposed the arrow feedback structure with the high order noise shaping. And then we also proposed the KD over C noise cancellation scheme that leveraged the bottom plate sampling in the hardware with the noise shaping SAR. With no constant on amplifier, and eventually we achieve a 13 bits of ENOB with only 0.4 picofarad of CN. And that's all for my today's talk. Thank you so much.